Hello! Today I'll be presenting the basics of forward kinematics. I'm going to assume that this is concurrent with the textbook and you have already read chapter 3 and we're just going straight at it. So, what is forward kinematics? It's essentially being able to calculate the end vector, using frames, angular velocity, distances, and, linear algebra. To do this, we're going to have to essentially look and guess, using a basic example. The reason why we're doing this is that it's a very crucial aspect of robotics. Once you know how to do this, a lot of things start to open up. Inverse kinematics, dynamic, chains, Jacobians, all that starts to open up and will be very useful during your adventure within robotics. So let's begin with this nice example. So here is the base frame. Let's call this base S, and here's the other frame. This is base B. Now, usually with different frames, as you've seen in previous chapters, they would probably be in different positions, different directions. However, in this example, Z and Y. So we're going to create a translation matrix, which will do the, what is the difference of rotation here? And as we see, they're the same direction, orientation, so it will simply just be the identity matrix. And also 0, 0, 0 down here, as you remember, is RP 0, 0. And you remember from previous chapters. Now, what is the distance? Well, we know this equals 1, 1, and this is also equal to 1. So, and we know that in the x direction, it's going to be consistent. So it's going to be 0, 2, 1, 1. So this is our translation matrix. This will be important as it will be the matrix we multiply at the end to get our translation matrix that we want between S frames to B frame. All right. So what do we do now? Well, we want to get, a space list, which will consist of the angular velocity and, the screw axis, matrix. This is what we want. And we also know that this V is equal to negative W x q. So in order to achieve this, we're going to have to essentially look at our chart and essentially guess, okay, this angle is rotating in the z direction, this is in the z direction, this is in the z direction. They're all revolve joints, and this is a prismatic joint, meaning that there is no revolve. So let's make a list. So we see here at 1, it's 0, 0, 1, because it's rotating the z. 2, 0, 0, 1, 3, 0, 0, 1, 4, 0, 0, 0. Now, given this is our frame, we're going to see the distance from each. If you look at here, it is, Q is going to be 0, 0, 0. So this will also be 0, 0 since, V is equal to negative Q. It's just going to be 0 given just basic multiplication. Now, the second joint area is by 2. So it's going to be 1. And given the cross product, it's just going to be 1, 0, 0. Same with 3, but with additional 2, it's going to be 2, 0, 0. And given this is prismatic, 0, 0, 1. Okay. We have that out of the way. Now what do we do? Well, essentially what we're going to do is we're going to do a skew symmetry matrix, which means we're going to take 0, x3, x2, x1, 0, negative x3, 0, negative x2, negative x1, 0. And with this, we're going to multiply it with the angles at each. So this is going to be 0, pi over 2, negative pi over 2, and this is equal to 1. So essentially what your thing is going to look like, let me give you an example of at least S1. So S1 is going to just look like it's going to be a skew matrix, so it's going to be 0, 1, 0, 0, -1, 0, 0, 0, 0, 0, and there's also the V, which is just 0, 0, 0, 0, 0, 0, 0. It's supposed to be a 4x4, and if you did that correctly, it should look like this. So you go from here, and we do the exponent of S1 times this. And for simplicity's sake, I'm going to program this. I recommend Modern Day Robotics, which is recommended in the textbook as well. It will simplify your life. And you do that for each of these points. So I forgot to add a S4, M. So once you get every, multiply the screw axis symmetric with the angles and do it to the exponent, what you're going to get is actually going to be coming out. Let me run it on my computer, and it's going to come out as TSB is equal to 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, -1, 1, 2, 1. This will be your TSB, and now I'll go back to why TSB is so important later on, but let's talk about body frames. Now, body frames are essentially the same as space frames when it comes to computation. The only difference is that it's going to be reversed in a sense. Let me just erase this. So M is going to stay the same, right? M is going to stay the same no matter what, but it's actually going to be a change in how we positioned. So it's going to be M, E, B, 1, E, B, N. All right, we have that. So what's the difference? Well, instead of going this frame, we're actually going to use this. So instead of, it's going to be what's it called? S3 is actually going to be 0, 0, 1, 0, 0, 0, given its position as an example, and then S1 is actually just going to be 0, 0, 1, -2, 0, 0, given it's in this, going this way. So essentially that, and then S4 doesn't really change given its position, so 0, 0, 0, 0, 0, 1, and then, what's I call it? S2 is just going to be 0, 0, 1, -1, 0, 0. Oh, sorry, it's supposed to be B. But you essentially do the same as what you did with the space frame. And if you did everything correctly, it should actually just give you the same result as the original TSB, which is, as remember, why did I delete it? Just the identity matrix rotation, 0, 0, 0, -1, 1, 2, 1. So this is going to be your TSB. Why it's important is essentially this will lead you to other concepts later down the road. So if you take the derivative of this you can get the velocity, which is, you get the velocity. You can also get stuff like this, which is very crucial for Jacobians and torques. And you can also just multiply, to find other sort of, translation matrices, which is useful given the nature of this robotics. You kind of want to have constants because it's chaotic, everything's a mess, everything's moving, so you want to have constants and just at ease. This is usually just a way to sort of make yourself seem normal, make yourself feel calm while doing this. So yeah, that was an example for kinematics. Hopefully it all went well and you see the usefulness. Good luck on your journey.